In this video, we are going to solve 3 problems and we are going to use accelerated frames in which to solve the problems. And in accelerated frames, Newton's laws do not hold as they are. For example, if you're in a car with an acceleration of a and you look out of the car, you will see a tree on which the net force is 0, but it has an acceleration of minus a. So you find that Newton's law is not valid. So how do you solve problems in an accelerated frame? The answer to this is, one answer is to use pseudo forces, but we have a better answer. This answer is due to Einstein, and Einstein's method works like this. Take a look at this little animation. This is the ground frame, which is an inertial frame. In this frame right now the cyclist is at rest. Let's give the cyclist an acceleration to the right. So now the cyclist starts moving faster and faster to the right. And what we are looking at is the accelerated frame moving with the cyclist. In this accelerated frame moving with the cyclist, you should see that the cyclist is at rest. Yes, the wheels are turning, but the cyclist is in the same place. The road and the hills and the rain, everything acquires an acceleration in the opposite direction to the cyclist. If the cyclist is moving with an acceleration a, everything acquires an acceleration of minus a. Now, when have you seen a situation where the acceleration of all objects is the same, as in this case, minus a, irrespective of its mass? Answer, gravity. In gravity, we find that all objects have the same acceleration. The cannonball and the feather fall together. So, Einstein's suggestion is this, that in this accelerated frame, you introduce an extra gravitational field whose acceleration is minus a. If the frame's acceleration is a with respect to an inertial frame, in this frame, you introduce an extra gravitational field to the left. And the acceleration of the gravitational field is minus a. And now you go ahead and solve the problem in this frame as though it is a stationary frame. Taking the ground frame as the inertial frame, in this frame, the elevator has an upward acceleration of 4 meters per second squared. Inside the elevator, we have a 4 kg and a 6 kg block attached to the ends of a massless rope, which goes over a massless pulley attached to the ceiling as shown. The blocks are initially held and then they are released. After how much time after releasing the blocks will the 6 kg block hit the floor of the elevator? That's the question. This problem is easily solved in the elevator frame of reference. In the elevator frame of reference, apart from the gravitational acceleration of 10 meters per second squared due to the earth, we also introduce an extra gravitational field whose acceleration is 4 meters per second squared downwards. That's because the accelerating frame has an upward acceleration of 4 meters per second squared. So in this frame, there is an extra gravitational field of 4 meters per second squared. So the acceleration due to gravity in this accelerating frame, which I will call G prime, is equal to 10 plus 4, that is equal to 14 meters per second squared downwards. Now, having introduced a new gravitational field, we can now treat this frame as a stationary frame and go ahead and solve the problem in the usual fashion. So let's draw the force diagrams for the 6 kg and the 4 kg blocks. For the 6 kg block, we have the tension T acting upwards and its weight, which is acting downwards. Its weight is mass multiplied by G prime, which is 14. That is the gravitational acceleration in this frame. And this is the tension T. Likewise, for the 4 kg block, we have tension T and its weight, which is going to be its mass multiplied by again G prime. This is tension T. Now in this elevator frame, the elevator is at rest, the pulley is at rest. We solve the problem as though it is a stationary frame now that we have changed the gravitational acceleration. So we'll assume that the 6 kg block moves down with an acceleration of a prime, and the 4 kg block moves up with an acceleration of a prime in the elevator frame. So for the 6 kg block, 6 times 14, that is 84, minus t is equal to 6 times a prime. And for the 4 kg block, which in this frame is accelerating upwards, it's going to be t minus 56, that is 4 times 14, is equal to 4 a prime. If we add the two equations, plus t and minus t cancel, I have 84 minus 56, which is 28, is equal to 10 a prime. So in the elevator frame, the 6 kg block is moving down with an acceleration of a prime, which is equal to 28 divided by 10 meters per second squared. Now in this frame, the 6 kg block starts from rest, taking down as positive. S, I'm going to write this in a different color. I'll write it out here. S, the displacement is 1 meter, taking down as positive, is equal to, in this frame, the 6 kg block starts from rest, ut plus half a, the acceleration is 28 by 10 t squared. So this gives us the time of travel for this 6 kg block before it hits the floor equal to, how much is that? This is 20 by 28, root of that. Root of 20 by 28 seconds. Of course, you can simplify that further. I'll leave it there. So in this problem, the wedge is free to slide on the horizontal floor. There is no friction. And there is no friction on the inclined part of the wedge either. So the block is free to slide down. Its mass is m and the wedge's mass is 4m. And due to the normal reaction force that the block exerts on the wedge will accelerate to the left. And the question is, what is this acceleration A of the wedge? Now the important thing to realize here is the following. As the block slides down, the wedge accelerates to the left, and after some time we will find that the wedge is here and the block has come down here. So you can see right away that the block moves down at an angle greater than theta. Theta is given as 30 degrees. You can see that the block actually moves down at an angle greater than 30 degrees, and we don't know this angle, which means you cannot use mg cos 30 as the normal reaction. You cannot say that the block slides down with an acceleration of g sine theta. All that goes out of the window. But what do we know? We know the following, that if you are on the wedge frame, that is if you're moving with the wedge, what do you see? You see a stationary wedge. And on the stationary wedge, the block slides down at an angle of 30 degrees. So the smart thing to do is get into the wedge frame. Let's do that. This is the wedge frame. In the wedge frame, what are the forces acting on the block? There is good old mg, force of gravity. There is the normal reaction, N, exerted by the wedge on the block. And apart from that, this is an accelerated frame. Its acceleration is a to the left. So therefore, in this frame, apart from mg, we will see an extra gravitational field to the right. And the acceleration of that field is a. And so what do we have? We have one more force acting on the block to the right, and its magnitude is ma. A is the acceleration of the wedge to the left. So in the wedge frame, there is a new gravitational field, ma. Now, in the wedge frame, the wedge is stationary. Now we have a simple fixed incline problem. Let's, as always, take x-axis along the incline and y-axis perpendicular to the incline. Let's look at the forces in the y direction. In the y direction, we have, that is perpendicular to the incline, n, and then mg has the usual mg cos theta in the negative y direction, minus mg cos 30 degrees is root 3 by 2. And MA, you can see, has a component in the positive y direction. If this is 30 degrees, this is 30, and so that is 60. So MA cos 60, that is MA cos 60 is half by 2. This is the net force in the y direction, and that's equal to 0 because there is no acceleration in the y direction in the wedge frame. Remember, once we have changed the gravitational field, we can now go ahead and treat this as an inertial frame, and we can write down Newton's laws in the usual fashion. So N is equal to, so we'll take the other two terms to that side. We have minus MA by 2. This plus MA by 2 goes that side, becomes minus MA by 2, plus mg root 3 by 2. Now let's come back to the ground frame and look at the force acting on the wedge. On the wedge, we have the normal reaction force exerted by the block by Newton's third law. This is also equal to N. And apart from that, there is a normal reaction from the ground, and there is 4 mg due to gravity on the wedge, but those are in the vertical direction. We are interested in the acceleration of the wedge in the horizontal direction. So we just need to find the horizontal component of N. So this is 30 degrees. So this is 30 degrees, and so this is 60 degrees. So N cos 60 degrees, which is N by 2, is equal to mass of the wedge times its acceleration A. So we get N is equal to 8 ma. So let's equate it here. N is equal to 8 ma. I have 8 ma plus ma by 2, that is 17 ma by 2 is equal to mg root 3 by 2. M cancels, 2 cancels, and I get A is equal to, the final answer, A is equal to, G is 10 root 3 divided by 17 meters per second squared. That's it for this problem. Let's go to the next problem. We know how to deal with fixed pulleys, but this pulley is accelerating downwards. So what do? Well, very simple. We get into the frame of reference of the accelerating pulley and change the gravitational field exactly as Einstein explained to us. And then we can treat it as a stationary frame, which means we can treat it as a fixed pulley. Let me show you. Let the acceleration of the 10 kg block be A, which means this pulley, which is free to move up and down, will accelerate downwards with an acceleration A. Now let's get into the frame of reference of this pulley. In the frame of reference of this pulley, we have, apart from the gravitational acceleration due to the Earth, which is 10 meters per second squared, we also have to introduce an extra gravitational field opposite to this acceleration of the frame. So we have to introduce an acceleration A in that direction, upward direction. So this is 10, this is A. So in the accelerating frame, the new gravitational field, we'll call it G prime, is equal to 10 minus A. Now let's go ahead and draw the free body force diagrams of the 6 kg block and the 4 kg block, just as we would do with a stationary pulley, because in this accelerating frame, the pulley is now stationary. And according to Einstein, once you have changed the gravitation, you can go ahead and treat it like a stationary frame. On the 6 kg block, we have an upward force of tension and gravity, its weight, which is 6 times the acceleration due to gravity in this frame, which is 10 minus A. And likewise, on the 4 kg block, we have tension T, and its weight is mass times acceleration due to gravity. Let's assume now that in this accelerating frame, in which the pulley is stationary, in this frame, the 6 kg block is accelerating downwards with an acceleration of A prime. And therefore, in this frame, the 4 kg block is accelerating upwards with an acceleration a prime. So let's write the equations. 6 times 10 minus a minus t, I've taken down as positive here, is equal to 6 times a prime. And the 4 kg block is accelerating upwards. Therefore, t minus 4 times 10 minus a is equal to 4a prime. Let's add the two equations. If we add the two equations, we get t and minus t cancel. 6 minus 4 is 2 times 10 minus a is equal to 10a prime. Now, we need to find the tension here so that from that we can find the tension in the rope, which upper rope, which will tell us the acceleration of the 10 kg block. So let's take this equation and plug it into this one so that we get the tension T is equal to, let me take 4 times 10 minus a to the other side, 4 times 10 minus a plus 4a prime, and you can see from this equation that a prime is 1 by 5 times 10 minus a. So 1 by 5 times 10 minus a. That gives us T is equal to 24 by 5. 5 times 4 is 20. 24 by 5 times 10 minus a. Now let's look at the force diagram for this pulley, for this accelerating pulley. What's the force diagram for this accelerating pulley? In the upward direction, we have a tension T prime because this is a different rope. And in the downward direction, we have T and T. So the net force on the pulley is 2T minus T prime is equal to mass of the pulley times its acceleration, but the mass of the pulley is 0. So T prime is 2 times T. So now as far as this block is concerned, we can write down its equation here. T prime is the force acting on it, which is 2 times T. So 48 by 5 times 10 minus a, that is 2 times T, is equal to 10 times a. 10 is the mass times its acceleration. So we now solve for a, and we get a is equal to 480 divided by 98 meters per second squared. So you can simplify this further if you like. I'm going to leave it here. Enough for today. I will see you in the next video. Bye-bye.